So I'm going to talk about the spectral spaces in minimal and other NIP theories. And I should start with an introduction, but I would like to fix some ideas before. And so just for the beginning, let me take a minimal expansion R of a real closed field R and take X a definable subset of Rn. I would denote by this the set of n types, complete n types concentrated in X, so the types that contains X. And in modern theory, we usually put the stone topology on this space of types, which are given by these basic open sets, which are of this form. So you take Y, a definable subset of X, and then you consider all the types that contains Y. Of course, this is Hausdorff and quasi-compact, and this is the natural topology to consider in the space of types from a model-theoretic point of view. But of course, you can put X inside the space of types by considering the type of an element over the type of R. But the truth is that X has a topology. I mean, R has a topology, the order topology. So X inherits a topology, but this map is not continuous. So you can solve this by considering another topology in the space of types that is called the spectral topology. That is easy, is just take as basic open sets in the space of types the sets of this form with U a definable open subset of X. This is called sometimes the minimal spectrum, and I will denote it by this way. So I will put a T if I am considering the spectral topology in the space of types. Now, this space of this minimal spectrum is again quasi-compact, of course, but it's no longer Hausdorff. Let me put an example of this. So take X, the real closed field, and let me zero the type of the zero, and 0 plus the type of an infinitesimal element A in a saturated model, infinitesimal with respect to R, and A minus A. In this topology, of course, 0 is closed because the set X equals 0 is a closed subset of R, but A plus and A minus are not closed because, for example, 0 belongs to the closure of 0 mass, 0 plus. Because, of course, if you consider an open subset, an open neighborhood of 0, it will contain both 0 plus and 0 minus. Okay? So 0 is in the closure of 0 minus and 0 plus. Of course, 0 minus, for example, 0 plus is not in the closure of 0 because, for example, you can consider the open set 0 infinity, that 0 plus is there, but 0 is not there. You can consider another example, take in this case X R2, and let's consider these three types, the green one, the red one, and the blue one. The green one is the type of 0, 0 over R. So again, it's algebraic, and of course, it's closed in this topology, in this spectral topology, because X equals 0, Y equals 0 is a closed set, closed definable set. The red one is the type of a tuple A0, where A again is a positive infinitesimal element with respect to R. So that's why I draw it in this way. So I'm in this line, but I'm really near 0, 0. And the blue one is the type of a tuple AB, where A is the infinitesimal I took before, and B is a positive infinitesimal with respect to RA, I mean, the model that generated by these two. That's why I try to draw it in this way, you know, since B is less than FA for every F definable over R. Note that the green one is 0-dimensional, the red one is 1-dimensional, and the blue one is 2-dimensional. And with this topology, not the stone topology, but the spectral topology, of course, you have that Q that is closed, so the closure, this closure, I will put T always to say that is the spectral topology, okay? So the closure of Q is Q because it's closed, and Q is in the closure of P because, again, each time I take an open set of the green point, that's what I'm doing here, take an open definable set, the red one is going to be there. And P is in the closure of L because if I take, you know, an open set of the red one, that is what I'm trying to do, the blue one is going to be there, okay? So I have this situation, and let me put another example. Again, take XR2 and consider these two unbounded types. P is going to be what's going to be this one, that is the type of A0, where A in this case is an infinite element, positive infinite element, so it goes this way. And Q says the type of A minus 1. Okay, both these two types are closed. Okay, are closed in this topology because, of course, the only type that is in this intersection, sorry, for the red one, the only type that is in this intersection, the sets of the form M infinity and Y equals 0 is this one. And this is closed, and this is an infinite intersection of closed. So this is a closed set, and the green one is also a closed set. Some examples. Fine. So it's not T0. Sorry, it's not T2. It's not Hausdorff, this topology. You have some points that are closed and another points that are not closed. That's the point. So it is not Hausdorff, but now the natural inclusion is continuous. Okay. Now it's this natural inclusion is continuous. And even this one is not a spectral space. Sorry, it's not Hausdorff, it is a spectral space. Okay? And what is a spectral space? Let me put the definition. A spectral space is a topological space S that satisfies these four conditions. So it is quasi-compact and T0. So T0 means that if I take 2 points, then I will find an open neighborhood of one of them such that the other point is not there, or the other way around. And in this case, this topology is T0 because in minimal structures, definable sets are Boolean combinations of open definable sets. This follows from the cell decomposition. So if two types have the same open sets, they have to be the same type. So if they are different, there must be an open set in one of them that is not in the other. It's T0. Okay. Of course, the set of all quasi-compact open sets in our case are the basic sets I put before. The intersection of two quasi-compact open sets is going to be quasi-compact because it's the intersection of two definable sets. And the last one is that it's sober, that what is called sober. That is that every non-empty closed and irreducible subset of S is the closure of a point that has to be unique because it is T0. This is another way of saying that it's T0. We do have two types such that the closure is the same. They are the same point. Okay. Okay. In our case, again, we have this property for the minimal spectrum. I'm not going to do it. It's just to define a type, a partial type in a familiar way. Okay. So the minimal spectrum is a spectral space. Doesn't mind if you don't retain the four conditions because I will try to work in an intuitive way. So Of course, it's important because spectral spaces is in the title, but what I'm trying to say is that I'm not going to use the properties in a hard way. So now that I fixed some ideas, let me put the introduction, the context. This construction, this minimal spectrum, as I put it, was introduced by Pillay in the 88. And his motivation comes from real algebraic geometry, because in semi-algebraic geometry, they had the same problem. And that's why Cost and Ra invented the real spectrum of a ring. But in minimal structures, this minimal spectrum has been used mainly to develop sheaf theories, minimal theories. So by several authors, Berarducci, Edmundo, Fornaciero, Jones, Pitfield, and Pillay. There is also a work of Peterzil where he compared this minimal spectrum with the real spectrum of the ring of continuous definable functions, because usually they are not the homeomorphic. So he compares them. And there is also an unpublished paper by Fornaciero that is really nice paper, where, well, he compared this minimal spectrum with some model-theoretic notions. As long as I know, this is somehow the use of minimal spectrum in the literature. So I would like to present some work that is in the line of this work of Fornaciero, in which we try to relate the minimal spectrum with different model-theoretic notions. So this is the outline of the talk. I'm going to say something more about normal spectral spaces in general, and then I will present three relations with model-theoretic notions. The first one is a relation of the minimal spectrum with the mu types, the second one with invariant types, and the third one with a Simon's retraction, a retraction that is in the NIP theory. So these two first relations are with the minimal structures, and the third one is in NIP theories, okay? Okay, so let me say something more about spectral spaces. Carral and Cost has a paper in the 83 where they studied normal spectral spaces. Well, the truth is that normal spectral spaces were studied before, but the paper by Carral and Cost is really a milestone in real algebraic geometry. And if S is a normal spectral space, what do I mean by normal spectral space? Okay, I have a spectral space that is normal as a topological set, so a topological space. That is, if you have two close disjoint sets, then you can find two open neighborhoods of the closed sets that are also disjoint, normal topology. So if you have a normal spectral space, the set of closed points that I'm going to denote by beta S.
Doesn't it have to be Hausdorff?
What?
Doesn't it have to be Hausdorff?
No. Yeah. Take 2 points, take the, yeah, okay. So take now the set of closed points, call it beta S. Usually this is called max S, but it's okay. I'm going to use this notation beta S. And this are the closed points of S. And since it's normal, S is normal spectral space, these closed sets, closed points are going to be Hausdorff and quasi-compact. Okay? Sorry? Since I not have Hausdorff property, I'm trying to make a difference. Sorry? Compact, this is compact. So yeah, Hausdorff. S is Hausdorff. Yeah, S is Hausdorff. So S, so no, sorry, S is not Hausdorff. Beta S is Hausdorff. It's compact. The usual. Yeah. So, and I have another property that if you take a point S in your spectral space, there is a unique closed point, and let me put it RS, that is in the closure of S, okay? there is a close point and a unique close point. So you have a continuous retraction from S to the close points of S. Okay, it's only because you have a normal spectral space. So in our situation, we have R a minimal structure or expansion of a real closed field. So in fact, I said that this is a spectral space, but the truth is that it's normal. Okay, it's normal. And when you try to prove that it's normal, you realize that you have to prove that X is definably normal. That's it. Given two definable closed subsets of X, there exist two definable open neighborhoods of the closed subsets that are disjoint. So, good. At this point, I would like to say that, of course, I'm going to work with a minimal structure, but this spectral topology can be considered for another structure, first order topological structures, as long as you have, for example, that definable sets are Boolean combinations of the open sets, or that is definably normal. And I mean, something that works in several valued fields, or even in weakly minimal. But here I have a question that I didn't want to put in the slides, is that if in weakly or minimal theories are definably normal. I was not able to find this in the papers in the literature, so if someone can give me an answer, because I don't know if it is true or not, I would be appreciated. So that was not of the top. So in our case, this minimal spectrum is a normal spectral space. So we have the closed points. I'm going to denote by this, which is Hausdorff and quasi-compact, so compact. And of course, we have X, a continuous embedding of X in the closed points, just because the algebraic points are closed. And we have a retraction from the minimal spectrum to the closed points. Okay? We have all this just because it's normal. Okay. So, but much more is true in our case of a minimal structure. So, for example, take P, a type in our space, and the closure of P must be finite, and the cardinality is bounded by the dimension of P plus 1. Moreover, if you consider the closure of P, you will have some types P0 to PL, and they will be ordered by the topological closure in this way. So you of course have the unique closed point that is P0. This is this is the unique closed point in the closure. Okay, and then you have what is called a sphere. Okay, so all the types in the closure are ordered by this inclusion of the closure, of the topological closure. And also the dimension decreases. So this has less dimension than this less than this than this. Okay. So what? No button? Why? Oh. Wait. So this is the example I saw before, if you remember. I mean, the ring one, the red one, and the blue one. So this is the case, no? This is for these three types. This is the closed type, and this is the retraction of the red one and the blue one. Okay, and they are ordered by the inclusion of the closures. So now that we know something about normal spectral spaces and more about the minimal spectrum, I want to present the first relation with the mu types. So this is about groups. So in each relation is going to be different from the other one. So now take this first relation is with groups. Take G, a group definable in R. So G is in Rn. I can assume, of course, by Pillay, I know this is a topological group, and by the work of Robson in the semi-algebraic setting, then extended to a minimal by Van den Dries, I can assume that G is embedded in Rn, and the topology, the group topology, really comes from the ambient topology. So then, Peterzil and Starchenko introduced the mu types. I will define it. So the infinitesimal type of mu of G is the partial type over R consistent of all LR formulas defining open neighborhoods of the identity. This is the infinitesimal type. And they define an equivalence relation in the set of in the space of types in this form. Take P and Q, two types. They say they are mu equivalent if there are realizations A of P and B of Q in some saturated fixed extension such that A B minus 1 is in the realization of the partial type in R bar. Okay, so this is a subgroup of G R bar. Okay, and we have this equivalent relations. Okay, so let me put an example again, and I will work with the same types. So fix in this case G R2 and addition. And of course, you can imagine the mu infinitesimal type like something like this, even bigger than the 0.00, so something like this. And of course, these types Q, P, and L, they have the same class, mu class. Okay, I will denote by mu the class of P in this equivalence relation. They have the same mu class. Okay. You know, because what I'm drawing, all three are inside this mu infinitesimal type. Another example. No, what's it? No, this is okay. Another example. If G is R2 plus again, now take the other two I considered before, the unbounded one. This is in fact it's an example of the paper of Kobe and Sergey. These two P and Q also have the same mu type. Sorry, are equivalent in this mu relation. Okay, because you can imagine that somehow the whole mu, the infinitesimal subgroup is here, and somehow you are multiplying P by this, so you get like a strength like this, and the green guy goes inside this band. Okay, so they have the same class. So these are some examples. Peterzil and Starchenko introduced mu types in order to extend the results on Peterzil-Starchenko subgroups. Recall that if you have a group G that is unbounded, then so for example, imagine this white board is the group that is clearly unbounded, and you have a curve that is going that way, so it's not converging in the group. Then they are able, Peterzil and Steinhorn are able to find a definable one-dimensional subgroup related to that curve. And in this work with mu types, they extend this, taking a type that is definable and something called mu reduced, and they are able, using stabilizers, to find also definable subgroups in a nice way. But that's not my point here, because in that paper they also discovered that mu types have interesting connections with universal compactifications. That's my point here. So they say, okay, let's put in the quotient space by these equivalent relations. They put the quotient topology from the stone topology, okay? And they prove that this is Hausdorff and quasi-compact, okay? And G, of course, you can, given a type G, you can consider the type of G over R and the mu class. And this is a continuous embedding with the topological, with the group topology here. Okay, that's what they prove. I'm not going to do this, but somehow in mind, this is true that it's continuous, because even here you put the stone topology, I mean the quotient stone topology, somehow mu has to do something about open definable sets. It's somehow like when you are working with a group, topological group, and you have a set and you multiply it by an open set, then you obtain something open. It's something similar what is happening here. Okay, that's why this is open. So continuous, sorry. In fact, G acts continuously in the mu types. But they proved, that's why I put here universal compactification, they proved that somehow if you have another compact set that G acts in X with another condition, then S mu goes inside this one. That's why it has a universal property. And also that is related to Samuel compactifications. So, but as you can see, we have G inside this one. This is compact, this is continuous. It's quite similar to the situation before with the closed points. So now there is a natural question, no? What is the relation of these mu types and the closed points of the minimal spectrum? That's the question, because the situation is quite similar. So this is the answer. Let me recall the notation. So recall that we have in the space of types with the spectral topology, it's a normal spectral space. We have a retraction from this one to the closed points. R is the retraction. And of course, you can consider the projection from the space of types into the mu types. That's take P to the class of that type. And this is continuous with the spectral topology, okay? Not only with the stone topology, but with the spectral topology. And the idea is because of what I said before. And in fact, you have the following, that if you take any type P, we have that the retraction of P is related in the mu equivalence relation with the type. And this is just because this map is continuous. So if you take the class of P, the preimage is going to be closed. So, and P is in that preimage, so the closure is in that preimage, so the retraction is in that preimage, okay? And furthermore, if P is bounded, then in the class of P, there is only one closed point that is the retraction of P, okay? So this is the situation as before. I mean, this picture. So they both three have the same class, mu class, and there is only one closed point that is this one in the equivalence class. Okay. So, and why bounded? Because in a bounded case, this is not true, because this is the example I put before. This is closed in the spectral topology. This is closed in the spectral topology, but they are not. They have the same mu class. So in the unbounded case, it's not true. So I will pass this. Okay. I will want to say something about the proof, but it's okay. So for example, if G is definably compact, then you have an homeomorphism of both objects, of the closed point with respect to the spectral topology and the mu types. Okay, this was the first relation. Then I'm going to try to explain the second relation, that is with invariant types. Okay, so now this is the situation. Take R and a minimal expansion of a real closed field, and take a saturated extension of R, and take X a definable set with parameters in R. Okay. So here we should, this one with a bar. Sorry, this is a typo. This is a bar here. We know that this is a normal spectral space with the minimal with the spectral topology. But it is now that we have these two models, R and R bar, is natural to consider the set of R invariant types. So these are the types that when I take an automorphism that fixes R pointwise, then sends the type to itself. And it's natural to ask about this set, the behavior of this set inside this. Sorry, again, this is a bar here. Sorry, so a bar should be here. Because in the stone topology, this is closed, this is closed inside this one. So it is natural to ask if it is also closed with respect to the spectral topology. And the answer is yes, is closed. Let me put the argument because we have all the ingredients. So take a Q, an element that is in the closure of the invariant tabs with respect to the topology, the spectral topology. Okay, since this is closed in the stone topology inside the space of types, you will be able to find just one type P invariant such that Q is in the closure of P. Okay, this is by quasi-compactness. So it is enough if we prove that given P and are invariant type, the whole closure with respect to the spectral topology is invariant. Okay, this is not enough to prove that. So let's do it. Take an automorphism of R bar that fixes R pointwise. Then this induces an homeomorphism in the minimal spectrum because being continuous is something that is first order definable. So this induces, in fact, an homeomorphism here to here. And as I said before, when you take the closure of P, this is a finite set that is ordered by the topological closure. So if I push this with sigma, I will obtain this one. If I push this one with sigma, I will obtain this one, and so on. But this one, sigma P is P because this is invariant, so this equals this. And they are ordered by the inclusion of the closure, and this is homeomorphism. So this one must be this one must be this one must be this one, and this must be this one. So all the closure are invariant. So this is because of we have this nice property that the closure is a sphere with respect to the inclusion and the closure and the topological closure. Okay, so the invariant types are closed. So in particular, they are a normal spectral space itself because it's closed with respect to the spectral space. But there is another prominent set of types here that are the finally satisfiable types over R. So these are the types that when I take a formula, then there are realizations of the formula in R. Okay, and again I'm asking, is this a closed spectral space? Because this is true this is true. This is true for the stone topology because I'm going to try to. No, it's okay. It's okay. I think they will speak. So.
Yeah, try black.
What? That one?
Try black.
Oh. I should write here because maybe I'm so again. So what I'm doing, I think this is worse. Sorry, this is well known, and that this set the finite or the coherent types are closed in the stone topology. Okay. So, okay, because just take a formula with parameters in R bar such that when I take the realizations in R is empty, then I don't want this formula. So these sets equal this one, these are closed in the stone topology. So this is closed. Okay, that's good, but what about the spectral topology? Well, the truth is that if I can put here open, that these one are open, then it will be okay, because if this is open, this is closed in the spectral topology, and then I have this is closed. Okay, and that's true. That's what I want to say. That you can put here that this one just to limit it to open sets, and this is so because of here. So it's okay, maybe. Oh no, again, can you? Okay, because of this proposition, recall that really finitely satisfiable types. This set is homeomorphic to the space of types of externally definable sets. Okay, so all that you want to do here, you can do it with externally definable sets. And you have the following, that this set is an externally definable set given, say, by W. That means that W is in R bar N and the intersection with Rn is set. Then there is a definable open set U in R bar N such that W is included in U, and set equals U intersection Rn. So the set is given by an open set. Not you can choose an open set that in fact contains the one you had before. Okay. So let me see a really stupid example of this. Imagine you have R and you have 0, 1 in R. That in fact this is definable 0, 1. You can define it with the closed formula 0, 1. Then you go to R bar and you can pick this U. So epsilon bar epsilon lives in R bar, is infinitesimal with respect to R, and you take minus epsilon 1 plus epsilon open, and if you intersect this one with R, then you obtain 0, 1, and this one is open and contains the W. This is a toy example, but the truth is that the proof goes through cell decomposition and make tricks of this kind. Okay, so this, even is a stupid example, probably is an important example. So because of this, you obtain that this one is closed, and not only that this is closed. So this one, the finitely satisfiable set is closed in this one, in the invariant ones, and the inductive structure topology coincides with the stone topology. So when you are working with finitely satisfiable types, the stone and the spectral is the same. So in particular, this set of finitely satisfiable with the spectral topology, of course, lives inside the invariant types and also are closed, because are closed sets, because with the stone topology, this one, the points is Hausdorff, the points are closed. Okay, so at least you are able to understand some closed points in the invariant case, the finitely satisfiable. So now again, there is a question here, is that, well, then what are the closed points of this one, of the invariant types? I mean, they are normal space, spectral space. We have a retraction from them to the closed points. So what are the closed points? Maybe are the closed points, which of course are the intersection of the invariant with the closed points of the space of types. So I wanted to say that these are the closed points of this one, okay? Because this one is closed in the space, in the non-minimal spectrum, okay? So what are the closed points here? Are the finally satisfiable ones? And the answer is no and yes. It depends on X and if the types are bounded or unbounded. But so if you assume that X is closed, so your set X is closed, then you will obtain that the closed points, that these are the closed point of the invariant types that are bounded. So that means that are bounded by some radius, okay, are exactly the finitely satisfiable types. Okay, are exactly the finitely satisfiable. So in particular, if X is definably compact, then the closed types, the closed points in the minima, in the closed point of the invariant types are exactly the finitely satisfiable ones. Exactly. And so we have a continuous retraction from here to here, okay? Because we have a natural retraction from your normal spectral space to the closed space. the closed points. So this is somehow another way to characterize finitely satisfiable types inside the invariant types from the topological point of view. Of course, here we are using Dolly work on invariant types. Here we are using it. Okay. So now how it's okay? I have 1 minute, 2 minutes?
Yeah.
5 minutes, 5 minutes.
10 minutes.
10 minutes, okay. So let me go to the third relation. So this is not about a minimal structure. This is about NIP theories. Pierre Simon introduced a new abstract retraction in the context of NIP theories. And in his paper, he says, this map remains rather puzzling. It would be nice to have a better understanding of it. For instance, a different construction leading to it. You know, okay. And if Pierre says that this is puzzle, it's not like I'm saying it's puzzle. I mean, so let me explain a bit, not the details, but what's going here. Take T and NIP theory and take a model M of T. And take now a saturated extension of M, like before with R bar and R, okay? The same situation. Again, take X a definable set with parameters in it. Okay. Now, Simon shows that there is a continuous retraction with respect to the stone topology. Of course, there is no spectral topology no more because we are in an NIP theory. It's only stone topology. He invents a retraction from the invariant types to the finitely satisfiable types. Okay, and I will not show the construction. He makes a construction usually using pairs, and he shows that there is a retraction from here to here, continuous with respect to the stone topology. And since this retraction is, in some sense, comes from a logic point of view, it naturally satisfies that the restriction of your type to M is equal to the retraction restricted to M. Okay. So now we have also a retraction that more or less goes to from the invariance to the finitely satisfiable. So it makes sense to think, okay, maybe they are going to be equal. But the truth is that they are completely different. I mean, for example, in our case, recall we have R, a minimal structure, R bar, an extension, a saturated extension. And for example, take this type, the 0 plus, that recall that is the type of a positive infinitesimal element. If you apply the topological retraction, it goes to 0. And if you apply the retraction of Pierre, it goes to 0 plus plus. And 0 plus plus is this type, the type that says, okay, I'm infinitesimal element, but I am greater than all the other infinitesimal elements. This is a finitely satisfied. So are completely different. Okay. But okay, we learned that retractions somehow appear when you have a normal spectral space topology. So now there is a natural question. Can we put here in the invariant types a new topology, not the stone one, a new one, such that it becomes a normal spectral space, and the closed points for this new topology are exactly the finally satisfiable over M, and that the natural retraction that I have from this normal spectral space to the closest points is exactly the retraction of Simon, is somehow natural, okay? And the answer is yes. And let me explain briefly what's the idea. Of course, it's not surprising that we will use honesty, no? This is rather in NIP theories. It's important by the work of Chernikov and Simon. Recall that given a formula theta x with parameters in M bar is honest over M if you take any other formula with parameters over M, okay? If this one, theta M, is included in this one, then in the M bar happens the same. Okay, then we say that this formula is honest over M. Okay, then Chernikov and Simon proved that for every formula, there will exist a formula theta that is honest over M that has exactly the same realization that the one you pick. Okay. So then we put the honest topology in the honest sets in the center of our topology, and the honest topology in the invariant sets, invariant types, is going to be the topology that has as a basis the closed sets of this form, where this is honest. So I'm not defining through open sets, but by closed sets, okay? Of this form with theta an honest set. And I will denote this set of invariant types with the honest topology with an H here. Well, okay, we proved that this is a normal spectral space, that the closed points are exactly definably satisfiable types, and that the canonical retraction to the closed points coincides with FM. So to be honest, we are not giving here really a new construction in the question of Pierre, a different construction, because we proved this using his idea of the pairs. But at least we are giving a topological context to the existence of the retraction. M is an NP, a model of NP, also NP fixed. Okay, sorry. So at least we are giving a topological context to the existence of the retraction. It's nice that usually you find the normal spectral space topology and then you get the retraction, but he got the retraction and then we were looking for the normal spectral space topology. Thank you. Oh, okay, sorry. No, it's okay. This is another way to understand the retraction, in fact, through honest sets. So a formula belongs to the retraction, the Pierre-Simon's retraction, if and only if there exists a formula in the type that is honest with the same realization. And finally, I will like to end with a question of Simon, that I think it's a nice question that we could not solve with all this stuff, normal spectral spaces, and it is still there, that it is the case that for given a type P, finitely satisfiable, the primage of P has cardinality bounded in terms of the cardinality of the theory and not on the model. So that's all. Thank you very much for the attention.
Thank you.